Hey everyone! So today my group and I will be talking to you guys about our senior design project, which as you can see is about reducing metal artifacts in ultrasound devices for spinal fusion surgeries. So before we get started, let's talk a little bit about us. So my name is Arielle, and just a few things about me. I love roller coasters, traveling, skiing, and going to the beach. One of my favorite things about Rutgers is all the fun events that Rutgers has. So in the top right corner, you can see me winning the ugly sweater contest at one of Rutgers' Christmas events. And then in the bottom right corner, you can see me having a lot of fun at one of Rutgers' late night events. And just a few of my hobbies, I love to sing. I play a ton of different instruments, including the piano and the drums. And I love to run. And I actually ran two of Rutgers' half marathons. And after I graduate, I'm going to be pursuing my doctorate in biomedical engineering. And you can see in the middle there me presenting my research at one of Rutgers' symposiums.
Hi everyone, my name is Hina, and a fun fact about me is that I used to have a pet duck and parakeets. And my favorite thing about Rutgers is the chocolate chip muffins from Gerlanda's in the Bush Student Center. They're really great value. They're these massive muffins, and I think they're only 150. And I also really enjoy Rutgers Gardens. My hobbies right now are watching Netflix, Hulu, and Amazon Prime Video, just to relax and numb my mind after a lot of homework and stuff like that. And my plans after graduation are to get a PhD in biology. And then I've just included a couple of pictures of me as a child and me pretty recently enjoying hummus, and then also a funny picture during exams, which hopefully, if you're looking closely, you get a chance to read.
Hi guys, my name is Ranya. A fun fact about me is that I have a black belt in karate. My favorite thing about Rutgers is 16 Handles on Livingston campus. They have a bunch of different flavors of frozen yogurt there. My hobbies include reading, watching TV, going to concerts, and traveling. And you can see two pictures of me in Athens and San Diego, just two of the places I've visited. And after graduation, I plan on working full-time in industry. The picture on the bottom right shows me, Hina, and one of our other classmates at last year's open house.
Hi, my name is Shunyao. You can also call me Joey. The fun fact about me is that I have a twin sister. My favorite things about Rutgers are the food places in Bush and Livingston campuses. My hobby is to collect all kinds of memes, and I plan to pursue a master degree in BME after graduation. Here are three pictures about me. The first one is me and my sister when we were very little. And the second picture is me during a Rusty Summer Science program in one of the BME lab. And the third one is my favorite meme for now, but I'm sure in the future it will be taken over by something else.
So now that we've talked a little bit about us, let's get on to our project. So imagine you're driving down the highway looking for your exit and you see this. Well, you can't read the sign, so you would probably miss your exit. Well, how about now? Now the image is very clear, so you probably wouldn't miss your exit. In our lives, it's really crucial that surgeons are able to see where and what they're operating on. Specifically for our project, we focus on the ultrasound, which as I'm sure you know is an imaging device. So just like the exit signs act as the roadmap for you when you're driving, similarly, ultrasound images act as the roadmap for surgeons in the operating room.
So to provide some background, our project focuses on using ultrasound in spinal fusion surgery, which is a minimally invasive type of spinal surgery. And as you can see from the graph on the right, it's becoming more and more common, specifically in people ages 65 and older. And the purpose of this surgery is to decompress the spinal cord by fusing the vertebrae together. And it involves inserting metal hardware into the spine, such as plates, screws, or rods, as you can see in the top picture. But the problem here is that metal artifacts are created by these screws or other types of metal hardware that create reflections in the ultrasound image. So it makes it unclear for surgeons to see what they're operating on. We're using ultrasound in our project as our imaging device, but there are others out there, such as computed tomography, or CT, and fluoroscopy. Ultrasound can do mostly everything that CT and fluoroscopy can do, with the added benefit of being radiation-free and more cost-effective. Ultrasound can also be used intraoperatively, meaning during the actual surgery itself, but as we mentioned before, it produces metal artifacts, which leaves an unclear image for surgeons to see what they're doing in real time.
So our goal here is to improve the ultrasound image quality. We plan to develop an algorithm in MATLAB to reduce the metal artifact from collected ultrasound images on spine for improving guidance during surgeries. And we aim to have the signal-to-noise ratio of the enhanced images higher than the accepted threshold, which is 10 dB. Here we also presented the three most important components in our project. The first is the spine model, the second is the ultrasound machine, the final one is our code. These are the pictures of our model for imaging the spine. As you can see from the pictures here, the medical screws acquired from the hospital were glued to the spine model. The whole thing will stick to the bottom of the plastic box. Then we filled it with water and took images using an ultrasound machine from above. After we collected the ultrasound images, we put them into the same folder with our code. Then the next slide will show you how the code works to enhance these collected images. By clicking the Run button, you will be directed to the graphical user interface here, and then you will be able to enter the image name here. By clicking Read the image, the original ultrasound image will be presented here, and then you can select the region you want to be enhanced. Double click. By clicking the enhanced image, it will show you 4 different images enhanced by the different filtering methods. For the auto mode, the image enhanced by method 4 can be presented here, and the reason will be explained later. For U-pick mode, you can basically select the one you think is the best according to your judgment. And to help with that, we also include the evaluating matrix here. The evaluating matrix include SNR, which is the signal to noise ratio, and also SSIM.
So like Joey just mentioned previously, our GUI works by taking in an original image like the one you see on the left, and you can see the issue with that. So what we really hope to see is just the bone surface, but unfortunately, because we're using ultrasound, you also get a reflection from the metal object, which is the pedicle screw. And so we take this original image and we input it into our GUI, and right now, there's only one filtering method being applied and then an output being released. But initially, when we started, we had 4 different filtering methods embedded into our GUI, and each one would release a different output picture corresponding to the method used. And our main goal at the time was to determine which method filters the best so that the bone surface is enhanced and the pedicle screw isn't really seen. And ultimately, we determined that this would be accomplished by method 4. And visually, maybe this is difficult to see, which is why we also began data collection so that we could quantitatively determine that method 4 is the best method to use. So here we have our data, and we collected images using a curved ultrasound device and also a linear ultrasound device. And what we did was we took images collected from both of these devices and ran them through our GUI, just as I showed you before. And we determined the signal to noise ratio. So what we have first with the blue is the signal to noise ratio of the original image. And then all of the other colors show you the signal to noise ratio of the images that were output after the original image had gone through all of the filtering methods. And what you see consistently with both graphs is that enhanced image 4, which corresponds to method 4, has the highest signal to noise ratio, which means that that image has the greatest clarity, and it even exceeds that of the original. So we collected roughly about 200 pictures total, and as we did our data analysis, we saw that image 4 has the highest signal to noise ratio, and that helped us to determine that method 4 is the best filtering method to reduce metal artifacts, and that's why we decided in our GUI to just have that as our one filtering option. So just to reiterate the impact of our work, the first thing that we did was we developed a novel intraoperative imaging strategy using ultrasound. What this allows for in orthopedic surgeries like spinal fusion surgery is it allows the surgeon to examine soft tissue around metal objects, and it allows them to do this during surgery because ultrasound can be used intraoperatively, and it results in 3D images produced in real time. And also because ultrasound is a cheaper imaging modality than others used, um, the use of this during spinal fusion surgery can decrease the financial burden on patient and healthcare systems because it drives down the cost of spinal fusion surgery, which makes it so that insurance might also be able to cover surgery. Another important benefit of ultrasound that we mentioned before is that it's radiation free. And what this does for the surgeon, the patient, and all the surgical staff involved is that it increases the safety of the procedure because no ionizing radiation is used. And then lastly, the thing that we hope to accomplish was we want to encourage ultrasound use in other orthopedic surgeries. So right now it isn't really used in orthopedic surgeries, and what we hope to do by showing its potential use in spinal fusion surgeries is to encourage other researchers to look into how ultrasound can be beneficial in surgeries like total knee arthroplasty or femoroacetabular impingement or other orthopedic surgeries where this can be beneficial. Thank you for watching our senior design presentation. We hope that you enjoyed it and got to see what we've spent this past year working on. And we also hope that you choose to attend Rutgers so that you can be able to do a fun project like this yourself in the future.